Hi there, Ms. Barber here. We have previously learned that derivatives can be used to determine intervals where a graph is rising and falling, or where the function is increasing or decreasing. Along with determining this behavior, we are also interested in the shape of the graph. The shape illustrates the rate of change of the increase or decrease. That is, the rate of change of the rate of change. For this, we will use the second derivative, which is the derivative of the derivative. The learning objectives for this lesson are: be able to find higher order derivatives, be able to use the second derivative to determine concavity, be able to use the second derivative to determine concavity, be able to find inflection points, be able to use algebraic techniques with derivatives to sketch curves, be able to apply the second derivative test to find local or relative extrema, and finally be able to solve applications involving the graph of a function's second derivative. A good question is, where might you use this skill? One such instance would be in advertising when looking for the point of diminishing returns. Healthy Endeavors estimates that it will sell N of X units of a newly developed heart function monitor after spending X thousand dollars on marketing as given by the function N of X equals negative 0.25 x to the fourth plus 23x cubed minus 360x squared plus 45,000 for x between 25 and 54 inclusive. When is the rate of change of sales increasing and decreasing? What is the point of diminishing returns and the maximum rate of change of sales? Let's get started. The second derivative. For y equals f of x, the second derivative of f, provided that it exists, is written f double prime x equals d dx of f prime of x. What this means is the derivative of the derivative. Other notations for the second derivative are d squared y divided by dx squared and y double prime. Example, find the second derivative of each of the following. A, f of x equals the square root of x plus 5x. When you see a square root of x, your first inclination should be to rewrite that with a rational exponent. So you'll have f of x equals x to the 1/2 plus 5x. Now we find the first derivative, f prime of x. To do so, we bring the 1/2 down, write it as a coefficient. X to the power of 1/2 minus 1 is negative 1/2, plus the derivative of 5x is 5. Now we take the derivative again. F double prime of x is, we bring the negative 1/2 down, so let's go ahead and write it out. The 1/2 from before, bring the negative 1/2 down, x to the power of negative 1/2 minus 1 is negative 3/2, and the derivative of the constant 5 is just 0. We clean this up a little bit, and we could write this as negative 1 divided by 4 for the 2 times 2, x to the power of 3/2. Since we moved the 3/2 to the denominator, we don't need the negative. Let's do part B. G of x equals 4e to the x minus e to the 2x. We first find the first derivative. So g prime of x is the constant 4, and the derivative of e to the x is just e to the x. Minus, now we need to take the derivative of e to the 2x, which requires us to use the chain rule. So we have e to the 2x, and the derivative of the power 2x is 2. We clean this up, so we get g prime of x is equal to 4e to the x minus 2 times e to the power of 2x. Let's take the derivative one more time to get us to the second derivative. So we have g double prime of x equals 4, the derivative of e to the x is just e to the x, minus 2. Then we need to take the derivative of e to the 2x, which would be e to the 2x. And applying the chain rule, we need to take the derivative of the power 2x. So that'll be 2. We clean this up a little bit, and we get that the second derivative, g double prime of x, is equal to 4 times e to the x minus the 2 times 2 gives us 4 e to the 2x. Continuing, for c, n of x equals negative 0.25 x to the 4th plus 23x cubed minus 360x squared plus 4,500. Let's find the first derivative. 4 times negative 0.25 is negative 1. Then we have x to the power of 3 plus bringing the 3 down and multiplying it to the 23. The product is 69. X to the 3 minus 1 is 2. Minus bringing the 2 down, product of 2 and 360 is 720. We have 1x left, and the derivative of the constant 45,000 is 0. Let's take the derivative one more time, which will give us the second derivative. So n double prime of x is equal to negative 1 times the 3 is negative 3x squared plus 69 times 2. That product is 138x. And finally, the derivative of negative 720x is just negative 720. Concavity. Concavity, or the shape of a graph, can be used to determine the rate at which a function increases or decreases over a specified interval. That is, concavity gives the rate of change of the rate of change. Example, consider the graphs of f and g. A. Discuss the difference in shapes of the graphs. F of x equals x squared, and g of x equals the square root of x. Let's plot a few points. Let's say for f of x, we'll plot at 0, 0.5, and 1. And for g of x, we'll do the same thing. We'll evaluate at 0, 0.5, and 1. Let's do the easy ones to compute first. For f of x equals x squared, at 0, 0 squared is 0, so the ordered pair is the origin, 0, 0. And at 1, f of 1 would be 1 squared, and 1 squared is still 1, so the ordered pair is 1, 1. Let's try for g of x. G of x is the square root of x, and at 0, the square root of 0 is 0, so ordered pair for g of x at 0 would be 0, 0. And if we evaluate at 1, the square root of 1 is 1. So for g of x at 1, the ordered pair is 1, 1. At this point, we see that both f of x and g of x are increasing. They're going from a low point of 0, 0 to a higher point of 1, 1. Let's see what happens in between. We will evaluate f of x at half, or 0.5. So 0.5 squared, we want halfway between 0 and 1. When you square that, the value is 0.25. So let's eyeball about 0.25, and connecting the points, we get a graph that's rising, but it looks like a bowl. You can sort of eat cereal out of that. Now let's evaluate g of x, the square root of x at 0.5. The square root of 0.5, or the square root of half, is roughly 0.71. So at halfway through 0.5, let's eyeball about 70% of the height. And when we plot that point, the graph is still increasing, but it bowls down. It looks more like an umbrella. So in discussing the shapes, okay, one bowls up, and when it bowls up, we typically call this concave up. And when it bowls down, looks like an umbrella, we call that shape concave down. Now, part B. Complete the table and discuss the relationship between the values of the derivatives of f and g and the shapes of their graphs. The derivative of f of x, which was x squared, is 2x, and the derivative of g of x, which was the square root of x, is 1 over 2 times the square root of x. Let's evaluate the derivatives at each of the given x values. So at x equals 0.25, the derivative, 2 times 0.25, is going to be 0.5. The derivative of f evaluated at 0.5, that's going to be 2 times 0.5, which is 1. The derivative f prime of x evaluated at 0.75 is 1.5, and the derivative f prime of x evaluated at 1 is 2. Let's evaluate the derivative g prime of x at each of those 4x values. At 0.25, the derivative is 1. At 0.5, the derivative is roughly 0.707. At 0.75, the derivative is approximately 0.577, and at 1, the derivative is exactly 0.5. What we observe is that derivative f prime of x is positive at all of those values, and the derivative value is getting larger. From half to 1 to 1.5 to 2, that derivative is increasing. Notice that that graph was concave up. G prime of x at those values, they're all positive, but the values are getting smaller. We go from 1 to 0.71 to 0.58 to 0.5. Notice that while the derivative is positive, the values are decreasing. For the function g of x, the derivative values of g prime of x are decreasing, and the graph is concave down. In summary, if the derivative values are increasing, the shape of the function is concave up. If the derivative values are decreasing, the shape of the graph is concave down. Definition of concavity. The graph of a function f is concave upward on the interval a to b if the derivative f prime of x is increasing on the interval a to b. The graph of a function f is concave downward on the interval a to b if the derivative f prime of x is decreasing on the interval a to b.